Hello everybody. Am I audible? Can I get a hello? Yeah, I hope I'm audible. And welcome to today's session on of the local hack week. So I'm Moise and I'm going to be your host for today. Yes, it appears I am audible. So hello everyone once again. We hope you've been enjoying all the sessions in this local hack week. Before we get to today's session, I have a quick announcement to make. In the WhatsApp group, we've sent a few links as well as a few instructions regarding how you can earn a few goodies by participating in this local Hack Week event. So those include stuff like challenges, uh, submitting feedback forms, writing blog posts, or just spreading the word. So in case you want to earn a few swags by participating and have fun while doing it, do check out the links and the instructions that we sent in the WhatsApp group. Now we come to today's session. So today's session is going to be special for two reasons. The first reason, all the events that we've done throughout this local hack week have either been regarding software or something related to software. Today's session is going to be about hardware and how you can use hardware in your projects. The second reason why today's session is special is because we have a very special speaker here with us. So everyone, please welcome today's speaker, Sudhansh. Hi, Sudhansh.
Hi everyone.
Hi.
Hope you're doing well.
Yeah, yeah. So let me give you a brief introduction about Sudhansh. So Sudhansh is a currently a final year student here at Trinity, and he is a computer-aided designer as well as a PCB designer. So he's also the head of the designing department of the technical advisory board at the Robotics Club. Apart from that, he's also the hardware head at Srinidhi Ascent, which is the entrepreneurship and innovation center at our college. So what we can take away from this is he really, really loves hardware, and he is an amazing person to be taking today's session. And Sudhansh, I hope you are having a great day, and I believe you can get started.
Yeah, okay. Thank you, Moise. Thank you for the introduction. Today I'll go through a few hardware tools which I usually use to design hardware. A few hardware tools, a few CAD tools as well as PCB design tools, a circuit building tool also. First thing, let me share my screen. We'll go through a bit of theory first. I hope my screen is visible. Hmm. Yeah, okay. Let me start. So, yeah. First of all, I'll introduce you guys to CAD and PCBs. CAD, coming to CAD, CAD is abbreviated as computer aided design. CAD is simply a concept which we use to design 3D models, to design 2D drawings, or even circuits before we manufacture in order to ensure that they work properly, to check the efficiency, to check the power dissipation, to check the force or the amount of stress a particular component can withstand. After getting the desired results, we go forward and we manufacture those things. Next, these are the uses and advantages we get by using CAD. We can increase productivity. We can present our ideas pictorially on a piece of paper, and we can show it to others to express ourselves. Then we can reduce the errors in real life. We can simulate and we can animate our own models using a few software tools. Then let's say I have an idea and I have to explain it to others, but I don't have a hardware representation of it. So what I do, I open one of my CAD softwares, I design it virtually, then I use it to explain to others. And next, yeah, these are the three major types of computer aided designing domains. First of all, mechanics. Next, we have PCBs and we have ICs. Coming to mechanics, also called as mechanical CAD. Here, what we do is we use some softwares to design mechanical parts. For example, engines of bikes and cars, else hydraulic arms, robotic arms, etc. Then we make them 3D, we make them fully functional using softwares. Then we assign materials to it. We customize the appearance, we customize the shape or size of the material. Then we apply simulations, we add simulations, we put the material under some stress, under some strain, under some force, and we draw reports from that. According to that, we can draw some really good insights on what you're manufacturing, what you're making, so that we can have a better uh, picture of the material when we actually manufacture it. And here are the softwares which are usually used for MCAD: Fusion 360, SolidWorks, AutoCAD, FreeCAD, and Tinkercad. I generally use Fusion 360. Next, we have PCBs. PCB design. Here, what we do is we take a circuit and we compact that onto a board. This is also similar to MCAD. We design the circuits, we enclose them inside a PCB, then we add simulations, we try to check out the power dissipation or try to check the heat resistivity or inductivity of the particular circuit. Then we simulate, then we move on and print the PCBs. So the circuit becomes much more smaller, much more compact. So the power consumption, the power dissipation, the overall cost of the circuit will be reduced. And here are the softwares which I usually use: KiCad, Eagle, Altair, and Altium. Next, we have ICs. As we know, ICs are miniature chips. What these ICs do is they possess some sort of complex hardware circuits inside them, mostly made up of transistors and diodes. For example, an IC, a microprocessor. For example, we have microprocessor 8051 and 8086, so microcontroller and microprocessors. Those are ICs. What they do is we take a wafer, then we use silicon and germanium to uh, you know insulate them with transistors. Then we connect those transistors to a specific functionality. So IC manufacturing is very compact and very miniature, also known as VLSI. Here also we do the same thing. We design ICs and then we simulate them. Then we print them on the wafer and we enclose them in a plastic or any sort of insulating material. Here are the softwares which can be used for IC manufacturing: Siemens, Cadence, Synopsys, and Xilinx Vivado. Xilinx Vivado is one of the softwares which my curriculum had. I'm from EC background. Yeah. So first we'll look into PCBs. Our motive of this particular session will be mostly relying on PCBs. So what is a PCB? PCB is an insulating base on which we draw routing using copper layers, and then we mount our components onto it. So the inclusion of wires will be less. So the more wires you use, the more power it dissipates. The lesser you use, the more power you can save. That is the reason we eliminate the wires totally, and then we embed those wires into the board. How and why, I'll explain. And these are the advantages which we get by using PCBs. The risk of short circuit and open circuit will be reduced, power loss will be reduced, and the complexity of the circuit will also be reduced. Here are the materials which will be used for PCB manufacturing. FR4 is a very redundant material. It's a very rigid material. FR4 stands for FR means fire redundant, and 4 means it's a glass epoxy. FR4 is the material which we use for making rigid PCBs which can be broken when bent. And coming to polyamide is used for flexible PCBs. Next, we'll have the composition of PCBs, what a PCB has to have in it to make it a PCB. Like basically, what are the parts or what are the layers a PCB will have? First of all, coming to substrate. Substrate will usually be made up of FR4 or polyamide, as I said. And over this substrate, we put on copper layers. Copper layer in the sense we wire those connections on the substrate. On top of that, we put another layer of solder mask. Solder mask is used to insulate the copper from the external environment. For example, it's not safe to put on an open copper copper outed PCB in the environment, right? Oxidization will happen and the copper might get damaged. On top of solder mask, we put on a silk screen. A few PCBs have a few naming conventions on that. Let's say I have a microcontroller, Arduino Uno. Arduino Uno has a bit of writing part on that. The title of Arduino Uno, then each and every single pin named behind that using some white sort of ink. That inking will be done on the silk screen, and it also gives the color and the glow of the PCB. Next, you have types of PCBs. All these types we'll look into detail. First type being single-sided PCB. Single-sided PCB is a PCB which has a substrate in the middle. On top of that, we have copper layer. I mean, copper layer is only on one side of the PCB. That is, those sort of PCBs are called as single-sided. Then we have double-sided. Double-sided has copper layers on both the sides. Both we have a substrate layer. On top, we have copper wiring. Underneath also, we have copper wiring. Solder mask and silk screen are mounted on top and bottom also. Next, we have multi-layered PCBs. Multi-layered PCBs are used to make the circuits even more compact. When you have a complex circuit, if the circuit is very huge and you have to put it onto a small surface, put it in a small PCBs, then you use multiple layers. Multi-layered PCBs are thicker in size, and it's also more complex and more costly to manufacture. As you can see, here we have consistent multiple layers of FR4 redundant material of substrate, as well as multiple layers of copper. Next, this is a separate classification of PCBs on what the material, what kind of material we're using for PCBs. First of all, rigid PCBs. Rigid PCBs are non-bendable. They are made on a stable, rigid surface, FR4, using FR4. And next, we have flexible PCBs. Flexible PCBs can be used in, for example, recently there is a huge booming in flexible electronics, where these kind of flexible PCBs are used. I mean, electrovoltaic cells and photovoltaic cells, solar panels are being uh, you know are being made as flexible materials. In those, we can use these flexible PCBs. Then we have rigid flexible PCBs, which is a combination of rigid and as well as flex PCBs. Then we have high frequency PCBs. In high frequency PCBs, the material which we use is same as normal PCBs. FR4 will be using, but the wiring will be done in aluminum. Yeah, then we have vias. Vias, uh, this is the concept which we use to connect the PCBs between the layers. For example, here we can see the plated through hole via. Consider a multi-layered PCB. It has 4 layers, and a through hole via, it starts from the top of the PCB and goes to the bottommost layer of the PCB. Next, we have buried via. Buried via, it cannot be seen. It is somewhere in the middle, embedded between the top and the bottom layer. Then we have blind via. Only one end of the via can be seen. The other is embedded between somewhere. These are the, these are the parts which we use to connect the layers of the PCB. For example, the through-hole via connects the topmost and the bottommost layer. The buried via connects the two layers between somewhere in between the PCB, and the blind via connects the topmost to the second layer of the PCB. These are the file formats which we use to design and manufacture PCBs. Coming to Gerber files and IPC files, these consist of the coordinates of the components and the wirings which we give in the software. I'll show you how to generate them. Then we have drill files. A few PCBs have holes to mount them onto something and drill them to make it steady. Those the size of the drill, the size of the hole, the diameter, the thickness of the PCB, etc. Those that kind of data will be held in drill files. Then we have bill of materials. A PCB will definitely use some hardware components on it, and what we do is we create a bill of materials. In which we include the list of all the components which have to be mounted on it. Next, we have fabrication drawings. Fabrication drawings include the size and shape of the material, size and shape of the particular component or a particular PCB, and all these files we zip. We design these files and then we zip these files and we send it to the manufacturer. Okay, this is it for the theory part. Next we'll be seeing how to design a PCB. Let me share my screen again. Yeah, all you have to do is go to this site, keycad.org. Keycad is the software which I use to design PCBs. So you don't have to create any sort of account in this. You don't have to pay anything. It's an open software. You can use it anywhere and in any device. And all you have to do is open this site and click on download. Select your operating systems. Mine is Windows, so I'll select that. Then yeah, then you'll see this interface. I generally use GitHub. As soon as you click on GitHub, yeah, as you can see, the application file will be will start to download. I already have this. As soon as you download that file and you run it, the software will be downloaded, and we'll start designing a few PCBs for now. And as soon as you open the software, this will be your user interface. First of all, these are the tools which this software has. First, schematic editor, symbol editor, PCB editor, footprint editor. The first five are the things which we'll be using the most. I'll explain briefly about the schematic editor and PCB editor. These are the tools which we normally use the most. First, all you have to do is click on file and new project. You have to name it. I'll name it as second. So yeah, as soon as you create a file, two sub files will be created. One for PCB and one for schematic. First you have to open the schematic. Yeah, here we'll be designing the circuit of the PCB. Circuit in the sense the basic connections of the PCB, the basic materials, the basic components which we are using. For that, uh, there is a symbol over here, add symbol. Click on that. All the libraries will be loaded. And this particular software can also run without any manually. Let's wait till the libraries load. Yeah. So these are the items. These are the all the components which KiCad has inbuilt in them. All the sorry. Yeah. These are all the components which KiCad has inbuilt. You can also customize and build your own components in this. First, let me take a resistor and drag and click. As you can see, I've placed a resistor. Next, I'll go with the capacitor. I'll place it here. Then I'll go with an inductor, L. Okay. Now I have three components. I'll design a circuit which doesn't make sense, but just for a demo. Let's rotate this. Okay. Yeah. Now let me connect these components together. All you have to do is hover your cursor at the terminals of the component. Just do this. Okay. Now my circuit is complete. Now, one important thing when it comes to PCBs, there are two simple terminologies we generally use in PCBs. First one is symbol, and the second one is footprint. What is the difference between them? The things which you see over here, R1, a rectangle for the resistor, and the two lines for capacitor, and the inductor symbol, these are known as symbols. Symbols are generally used to represent the particular component. Coming to footprints, footprints represent the size and shape of the component which will appear after designing and manufacturing the PCB. For example, double click on this resistor. Now here, as you can see, there is an option called as footprint. We open the library and then I type resistor. As you can see, these are all the footprints which we have. Each and every footprint has, wait a moment. Each and every footprint has a different size and shape. As you can see, it is changing. So you can use any sort of footprint, giving space to your own reference, or what footprint you need to use, you can use. I'll be using the first one, the footprint which I normally use. And every single component has its own footprints, so you can customize them as you wish. You can even design your own footprints also in this software. Capacitor, yeah, you can see capacitor also has different sizes and shapes. I'll use the first one for now. Click on OK. Same goes with the inductor. Inductor also, I'll assign a footprint. And yeah, click on OK. Now that I have all my components and I've wired everything together and I've assigned footprints also, I'll just save it for now, and I'll go to inspect and I'll run ERC, electrical rules checker. It will check if I have any errors or warnings, any short circuits or open circuits in the circuit. Once there are zero errors and zero warnings, you can proceed. Now we have to close this. Now we have to export this into the PCB editor. This is a schematic editor. As I said, we design just the circuit over here. In PCB editor, we design and customize our own PCB. So for that, we have to click on File, then click on Export, then click on Netlist. Now click on Export Netlist. Name it as you wish. I'll name as CH schematic, and I'll click on OK, and I'll click on Save. Okay. For now, my work with schematic editor is done. I'll save it once more and I'll minimize this. Now, see. Second, this is the project file which I've created. Under this, we had a PCB file and as well as a schematic file. But now I have a backup file as well as a .NET file. The .NET file represents the netlist file which we just exported from the schematic. So now I'll open my PCB file. Yeah, this is the interface for the PCB editor. Here what I'll do is I'll click on File, I'll click on Import, I'll click on Netlist. Now click on this file and click on the .NET file which we just exported from the schematic editor, and click on Open. Now we have opened it. We have to load and test it. See here, total warnings are 0, errors are also 0. So we can proceed. We can proceed with that. Next, we click on Update PCB. Click on Close. Now we can see these are the components which we selected, and these are the footprints of them actually. And once you print the PCB, this is the size, original size of the components which will be appearing, the number of terminals and all. Now, yeah, this is the inductor, resistor, and capacitor. So if you want to realign the components, just click on the component and click on M. You can simply, just a moment, click on M and you can move it. You don't have to drag, just hover the cursor and you can move. And next, I want my resistor to be more towards the right. So yeah, no, over here. Then I'll move my capacitor also. Click on M and I'll move it. Okay. Yeah, now that I've moved, we'll start wiring also. As you can see, these faint blue lines, these represent the connections which you gave in the schematic editor. Apart from that, you have to manually wire also. You can use external plugins, but plugins can't be customized. That is the reason I'll try to manually wire them. So as you can see, we'll use the route tracks over here. Select f.cu copper wiring, and I click on this terminal and I'll simply wire them together. Done. Now that the wiring has been done, the most important part of the PCB is the size and shape of the PCB, the edges of the PCB, how you want to customize them. I'll explain how to do that also. Now you can click on line and select the material as edge cuts. Okay. Now I want to assign some random shape to it. For example, like this. Done. Okay. So now for now, this will be the outline of my PCB. All I have to do is save it, click on file, and save. Next, you have to go to view, 3D viewer, and this is how my PCB will look after I manufacture it, after I print it. Okay. So now, as we are done with the PCB, now I'll show you how to export this PCB and zip the files. Click on file, and next click on fabrication outputs and click on Gerbers. So you'll find a pop-up, errors are 0 and warnings are 0. So click on generate drill files, generate drill file, close. Now you can close this and minimize this, and you can see drill files. I've generated the drill files. Next we have to generate Gerber files also. Let me show. Click on file again, fabrication outputs, Gerber outputs, plot these ones. As soon as you see the done, close. Now minimize this. See. So for the copper wiring, for the edge cuts, for the silk screen, for each and every single component, a separate Gerber file will be generated. All you have to do is select all these files, zip them, and send it to the manufacturer. The manufacturer will decode these Gerber and drill files, and he'll print the PCB on the material which you intend to print. That's how PCB. That's how PCB designing and PCB manufacturing works. I hope I'm clear for now. Yeah. Any doubts for now? Uh, does shape of PCB and layout of components matter? Like, can different components interfere with each other if placed too close? Yeah, we have a set of rules, set of protocols which we need to follow. For example, the distance between two separate copper lines on the PCB should be around 0.2 mm. Anything lesser will cause a lot of interference between them. That's you have to take care of that also, and the edge of the PCB also. I mean, the distance between any component or any wire with the edge should be around 2 mm. I mean, did you get it? The I mean, the distance between one of the wires, the outermost wire and the outermost edge of the PCB should be around 2 mm. Anything else? Any other? Did I clarify the route? I guess so. Yeah. Let's move forward. We'll look into MCAD a bit. We'll design a few mechanical parts also, and we'll try to simulate them if time permits. And as I said, I use Fusion 360. For Fusion 360, you have to open this particular site. I'll share my screen just. So yeah, this is a site which I was talking about, autodesk.com. Here you have to first create your account for this, and next we'll look into a few products which Autodesk has for us. Then click on this products. We have AutoCAD, Revit, Civil 3D. Autodesk provides these software tools for designing mechanical parts, for designing architectural drawings, or even design graphics. So yeah, look at here. We can see Fusion. This is the software which we'll be using. So I'll click on that. Yeah. As soon as you click on Fusion, you'll see the details. A brief description about the software. Then you'll see a bit of pricing. Don't worry. You can access this completely free of cost if you're a student. I'll tell you how to access that also, and then a few partners and all, a few designs. So yeah, next up click on download free trial. Yeah, then you have to choose the sort of purpose which you'll be using Fusion 360 for. We'll be using for educational purpose, of course. So click on Autodesk Fusion for educational use. Click on educational community, and these are all the softwares which Autodesk provides. Whole lot of softwares. Most of these softwares are related to mechanical engineering, architecture, and graphic designing, UI UX designing, etc. We'll select Fusion, and then we have a subscription plan. I have already a subscription, so I click on select. Then you have to fill your details. Product details will be accessing Fusion 360, one quantity, one single product. Then the customer details. Then here, from here, it's pretty critical. You have to select your schools or colleges address. You have to give it carefully. Then you have to give the school's information. If it is university or a private college or a school, you have to select. Then give it the name, and next you have to copy paste your institution's website. Then the graduation date of yours, and click on OK and confirm. Continue. The educational verification is also a pretty critical step in this. Here it will ask the scanned copy of your ID card of your institution. Once you scan that and once you submit, within 48 hours your ID card will be verified, your institution will be verified, and within 48 hours you'll get the confirmation about your account. Once everything is all right, if your all the provided documents and provided data is well and good, then Autodesk will provide 1 year free trial, for 1 year free subscription for you, which lasts for 1 year. After 1 year, if you are still in the school, if you are still studying, or if you are still a student, then you can upload your ID card again, and you can access for 1 more year. Okay. Then once you submit, you'll get an option to download the installer file. Once you download it and run it, the software will be downloaded. And once you open the software, let me share the user interface of the software first. Yeah, I hope my screen is visible. So this is the user interface which you'll get once you download the software. I mean, you have to sign in again. The account which you have created in Fusion, in Autodesk, you have to sign in with the same details. Once you have signed in, this is the user interface which you get. A whole lot of tools and all. Yeah. So first we have create tools, then modify tools, assemble tools, construct tools. So first thing, in this Fusion 360, you can design 2D sketches as well as make them 3D also. How I'll show you. First, you have to click on create, then click on create sketch. Then you click the plane on which we have, as you see, we have in 3D plane, we have X, Y, Y, Z, and ZX plane. select whatever plane on which you want to create the 2D model. I'll select this one. Yeah. Now click on create again. Here you'll get a few 2D diagrams, options of 2D diagrams. I'll select a circle, center diameter circle. Click in the center and drag. You can give it a measurement also. Content. Now I have a 2D sketch of a circle. Okay, got it. Now next click on finish sketch. I have a 2D circle. Now how do I make this 3D next? All you have to do is click on create again, then click on extrude. The extrude option is used to add another dimension to the 2D model. As you can see, I have an arrow over here. I can move this forward, making it 3D. Else I can move this backward also. Okay. For now, I'll move it forward and I'll give it a dimension as 5. So now I have, yeah, now I have a cylinder. I made a cylinder out of a circle now. And next, I'll show you how to make it, how other tools also work. We have hole. Hole is used to make this hollow or create a single hole between uh, the surface. I can move it. I can simply make it big. Let me move it to the center. Yeah, and I can also customize the depth of the hole also. And if I click on OK, as you can see, the cylinder is hollowed now. Okay, and next we'll see a bit of modify tools also. In modify tools, we have press pull. Press pull is used to increase or decrease the size of a component. Uh, and now let me select this. As you can see, select this face, and I can increase the size or decrease it. Okay, that's the use of the press pull option. Next we have fillet. Fillet is used to smoothen up the edges. As you can see, it is not smoothened now. As soon as I push the arrow, the surface smoothens up. I mean, a curved surface will be appearing. Then we have chamfer. Chamfer doesn't necessarily smoothen it up, but it just gives it a planar sort of surface. Let me show. You see, yeah. This is the difference between a fillet and chamfer. Fillet will simply smoothen up, curven up the surface, whereas chamfer just cuts it off. Okay. Done. Next, we have shell tool. Shell is used to hollow up a surface. Then we have draft. Draft is used to cut a surface off, pull a particular face into a single direction. Scale. Scaling is used to increase or decrease the overall size of a material. The only difference between press pull and scale is press pull only changes one single dimensions of the material, while as scale changes overall all the dimensions of a material. For example, I'll click on scale. I'll select this. As you can see, the diameter, the thickness, else the length of the cylinder, everything changes. While as when I use press pull, only one of the parameters can be changed at a time. That is the difference between press pull and scale. Combine is used to combine two bodies into one single body. And next we have all these. We don't use a lot of these tools. If you want, you can explore it a lot. This is actually a pretty fun software. And next we have move or copy. Move or copy is used to move a surface here and there in the plane, this way or this way. else I can simply rotate in the direction which I want. That is the move option. And then if I want to create a copy of it, all I have to do is select the surface and click on create copy. As soon as I click on create copy, if I pull it in any direction, another copy of the material will be forming. Okay, that's the difference between move option and copy option. Next we have the most important ones: physical material and appearances. Physical material changes the overall structure. I mean overall, internal structure of the body. For example, it's loading. Wait a moment. Yeah, as you can see, there are a lot of materials which we can use: ceramic, electronics, liquid, metal, etc. The purpose of changing the material is when we apply simulations on this. Mechanical components mainly depend on the material on which they are built up. Okay. Now, if I use a plastic material for this particular component and I run simulations on it, the results will be different. Whereas if I use aluminum or steel, the results will be far more different, or maybe far more better also. That is the reason we need to check whether we are using the right material or not. I'll use let's go with copper, cast copper, drag and drop on both of them, and click on close. The only difference between physical material and appearance is physical material changes the component internally. I mean the whole component will be changing its material, whereas appearance, if I select appearance and if I select some material, the component will be coated in that material. For example, let me take steel again. Here the internal structure or internal material doesn't change. The internal material is still copper, but just the outermost layer is made up of steel now. I hope I'm clear. Now we can close this. Now I've created two bodies now. Okay, for time being, I'll delete the second one. We don't need it for now. Click on delete, delete. Okay, now I have a singular body in my canvas. Now I'll show you how to join two bodies. So for that, I'll need to create another body. So we'll click on create sketch again. I'll select a plane. Now I'll create a cylinder which I need to fit that into the previous body. So I'll click on circle again, circle, center diameter circle, and I'll select the center and I'll drag. Okay. Now I'll click on finish sketch again. You see, there's a circle which I just drew, and we need to make it 3D again. And guess what? We have to use extrude again. So click on create and click on extrude, and then just press and pull, and I'll give it a random number as 20. So yeah, 20 centimeters, new body, and okay. One important thing is when you extrude a particular component, these are the operations which you can see: join, cut, and intersect. These options come to use when you try to extrude a body over another component. Okay. For example, if you join and if you select join and you select and extrude your current component over a older component, then those two components will join and merge into one single body. Okay. Next, if I use cut, the current extruding which I do, it will simply cut off the material of the previous body. I'll show you an example. Let me just draw a bigger circle. Okay. Now if I try to extrude this into the previous component which already exists, Okay, see the operation cut. Click on that. The middle portion where I just extruded, it will just vanish. Okay, and if I select the same circle again and I extrude it again, but now I use join. If I extrude and click on OK, all the previous component as the current and the current component will simply merge into one single body. Okay, so you have to be careful over here if you don't want to mess up your previous components. I'll simply go back and I'll create another circle. We'll continue with joints. And I'll extrude it, making it, and I'll select new component. So the difference between body and the component is a body is a body forms when you extrude one single sketch one single time. Okay, and if you combine multiple bodies, then that will form into a component, and you have to make sure that you extrude it as a component, because you can apply joints only to components. Bodies cannot be joined together using the joint option. So I'll extrude this as a component now. Sorry, I made a mistake over here. I extruded the first cylinder as a body. You can edit that again. Click on edit feature and then click on new body. No, no. Okay. We'll just design another cylinder for that. Don't, no worries. Create sketch. Okay. And I'll select this and I'll extrude this. So now I'll select new component again and I'll click on OK. This body is of no use, so I'll delete it for now. Delete. Can't delete again. So now I have two separate components on which I can apply joints. I'll simply move this backward. Move and copy, and I'll move this to separate them. Okay. Now I have two components. This is component one, and this is component two. And on these two bodies, we'll try to add a few joints. Okay. For that, we have to click on assemble and click on joint. Okay. First thing, I'll show you the motions or the types of joints which we have in Fusion 360. First of all, we have rigid joint. Rigid joint will simply join the two components, but there will be no movement in that. And coming to revolute, in revolute, the internal component or the external component can revolute uh, inside or outside in clockwise or anti-clockwise direction. That also we can customize. Then we have slider. In slider, you can simply move one component inside and outside the body. Then we have cylindrical. Cylindrical motion includes cylindrical and pin slot are much more common. Cylindrical and pin slot, they are a combination of slider and revolute. Okay, coming to planar, in planar we rotate a component in alignment with a single plane. And next come to ball. For example, we have the socket joint in our shoulder. The same sort of rotation, the same sort of movement we can give to the components. So now I select the first component, which is this, and I'll select the second component, which is this. Okay. Now I'll give them some say rigid, it won't move. Revolute, it's actually revoluting. Slider, it will move in and out. Next we have cylindrical. It rotates as well as moves in and out. Pin slot, much more similar but in a different axis. Next we have planar. I'll show planar again. Next we have ball. Rotates just similar to our shoulder. For now, let's select revolute. As you can see, the revolution. So this is how you design and join a few things. Let me show one of my projects which I made of my by myself. And yeah, it looks a bit complex, but is very simple, very easy to make. All you have to do is ensure that your measurements are precise. Just design stuff and join them properly. And these are all the joints which I use. A lot of revolute, and here are all the components which I used. And you can also move this here and there. Let me show. You see, if your joints are properly functional, then you can also create these kind of movements and also generate a few animations with them also. Okay. I'll explain a few export types also for this. Let me save this. Yeah, it's a bit laggy. Yeah. Now I have saved the component. Now to export this, you have to click on File, then you have to click on Export, and these are all the files which Fusion 360 supports for exporting. The normal one is the most commonly used in Fusion 360 is F3D archive files, and for 3D printing we use STL files, STL files as well as OBJ files, which can be used for 3D printing. And I'll select STL and click on Export. Now my now my file will be exported directly into the folder which I choose, and that file can be imported into a slicer or a 3D printing software from which you can start your 3D printing. Okay. Now, what else do we have with Fusion 360? And we have this timeline. Timeline is a pretty handy tool which you can use. For example, I've made a I've done with my project. I'm done with my, but I have to edit one single feature which I did long ago. Okay. For example, uh, this particular tool, this particular operation I did a long ago. I mean, this particular tool I extruded it before extruding this. Okay. So if I want to edit it, I can simply right click on this option and click on edit feature. Here I can edit it again. For example, if I want to extrude it two sides, I can extrude. Or if I want to make it symmetric, I can make it symmetric. If I want to change the profile type, I can. If I want to change the distance or the taper angle or the operation also, I can change everything, and I can click on OK. But the later operations won't change again. The later operations will be remaining intact. That is a positive thing of about Fusion 360. Other advantages are this particular software is uh, reinforced with cloud. I mean, I can do this one of my projects in one single device. I can open Fusion 360 in other device, log in through my account, and access the same project in the other devices also. Okay, and there is also a mobile version of this software. In the mobile, you can use it to export and view your models, but you cannot edit them properly. So it's better to use a PC or a laptop for better comfort. That is with CAD and Fusion 360. We'll move further into circuit designing. Okay. Any doubts with Fusion 360? I hope I was clear. Is this used for 3D printing? If yes, then how do you change size of model in real life, like length and centimeters? You cannot change the models. Yeah, this software can be used in 3D printing also. Any CAD software can be used. All you have to do is export the software in STL files or OBJ files. And coming to your second question, how do you change size of model in real life, like length in centimeters? After 3D printing, there is no way to change the dimensions. If you want to change the dimensions, you have to change it in the software. Then you have to export it again as STL file or OBJ file. Then you have to import that file into the slicer or the 3D printing software. Then you have to reprint it again. There is no other way to change uh, the. Okay, hello. Would you recommend FreeCAD? It looks complex. Fusion 360 is the simplest one actually. FreeCAD is even more complex, as I have seen it. I've seen it once, but I didn't really think that it would be beginner friendly. Fusion 360 is better. This has, and as you can see, every single option, when you hover your cursor over them, every single option has a bit of description also. If you want to, if you are a beginner and you want some tutorials, this has inbuilt tutorials also. Sweep, again, it has a tutorial what that tool does. Then you have loft, rib, etc. That's I think Fusion 360 is better for beginners, not FreeCAD. I hope I'm clear. Done. Yeah, let's move on. We'll look into Tinkercad. Tinkercad is also one of the. Let me stop my screen. Yeah, Tinkercad is also one of the tools which is provided by Autodesk Fusion Autodesk. Tinkercad is completely free. You don't have to use any sort of educational license or your ID card verification for that. You have to access it anywhere. All you have to do is create your own account in that. I'll show how to use it and how to create a few circuits and how to simulate them also. And coming to the important thing, the softwares which I just explained, Fusion 360 and KiCad, these softwares can also be used for freelancing also. If you're a student and you want to earn some money without actually getting into a job, you can simply freelance. You can find opportunities on LinkedIn at a few CAD and PCB communities also. So it's better you can start it whenever you want. Just sit down and whenever you have free time, just sit down, create an account, download the softwares, and you can tinker with them. No worries. And these softwares don't have any sort of project limit. You can create any number of projects you want. Okay? There is no limit. Next, we'll go with Tinkercad. Okay. Now, once you create your account, here this is the user interface which you'll get once you open the once you open the tool. This is not exactly a software; it's a web tool, website-based tool. Here you can create code blocks, you can create circuits as well as 3D designs also. But 3D designs and code blocks, it's not very efficient for this. But circuit designing might be a good option in this particular tool. So yeah, here are some of the designs I've made. I generally use this for circuit building. These are all the circuits which I made so far. Whenever I be free, I'll simply open Tinkercad and start building circuits. This is also a fun tool which you can use for your projects as well as for passing your time. We'll see how to generate circuits over here first. So once you create a new circuit, this will be the canvas where you can build your circuits. Uh, let's build a simple switch circuit. Maybe I'll take an LED, then a resistor, then a switch. So we don't need a switch actually. Oh yeah. Then a battery. Three volts battery should be enough. Then we simply connect the circuits. Okay, and then we assign the value to the resistance. 330 ohms should be enough. I'll change this kilo ohms to ohms. Now, like this, you can build your circuits. But the main thing with this particular Tinkercad is you can simply code the components also. For example, if you're using a microcontroller or a microprocessor to simulate your circuit or simulate your project, then you can simply code that and you can run simulations also. I'll show you. I'll I'll go with Arduino Uno. Click and now I have an Arduino Uno. Arduino Uno is the most basic and the most commonly used microcontroller based development board. On this, we have 14 digital pins and 6 analog pins. This particular board can be used for making beginner projects, for example, traffic lights, else your simple attendance marking system. From those basic projects, you can also use this to implement complex communication protocols also. For example, serial peripheral interface, else inter-integrated circuit protocol, else UART those are just a few examples. A pretty handy component this is. It comes at around 600 to 700 rupees outside. You can just buy it and you can use it for your daily use projects as well as a few complex projects which you can use in your major projects in your coming years also in third or fourth years of your engineering. Okay, now this is the complete board, and through this port you give power to this. You connect the USB cable to your laptop and you connect the port to this, then it will be starting. And next, this IC which you see, black color IC, this is Atmega 328P. Atmega 320p, this is the actual microcontroller. Okay, the microcontroller is expanded and it is made into a single board. Okay, inside this microcontroller we have timers, we have counters, we have a microprocessor, miniature microprocessor, we have a bit of storage also inside. As you can see, these are the power pins, analog pins, and then we have digital pins. Now the TX and RX, these two pins are used for implementing communication protocols. Those can be wired protocols as well as wireless protocols. Okay, now this particular microcontroller has an inbuilt LED at pin number 13. 13 is the digital pin. 13 is digital pin. This has an inbuilt LED also. So we'll try to code that. I'll show how to code that to you also. Click on code. Here you have three options. You can either code in blocks, else you can code in blocks as well as text, else you can code in just text. I click on text and continue. Here you have a default code for the inbuilt LED. I'll explain how the code works. So the code for Arduino works like this. It has two main driver codes, void setup and void loop. I mean, those are the two main driver functions which have to exist in the program for Arduino Uno. The first void setup is used to define the pins, and the void loop is to write the logic for the pins. Okay. For now, here the 13th pin, which is the built-in LED pin, I define that pin and I give output from that. Okay. uh, Digital pins can have two functions: either give output or take input. You'll give it input here if you are using some sort of sensors, external sensors from which you have to take input. Then you can simply give the pin here, let's say 12th pin, and you can write here as input. So you're just informing the microcontroller that you have to take the input or output from this particular pin. Okay, let's keep it unchanged for now. Next, in void loop, you'll write the logic. These are the like, you have to be careful with the syntax also. The pin mode, it is case sensitive, so pin should be in lowercase, m should be in higher, and ode should be in lower. Then you have to be careful with the semicolons also. And inside void loop, you have to write the uh, logic, main logic. Here you have digital write. 13th pin of the Arduino Uno is a digital pin, so you have to uh, give it as digital write only. If you are using some sort of analog pin, then you can give it as analog write. Okay. Now next, digital write. Then we in the brackets we put the pin name. Pin name, you can include it as 13, or else LED built-in is fine. Then normally the output from the pin will be low. So so defaultly the LED will not switch on. So for it to switch on, we'll just give it as high. Okay. Then we'll give it a delay of 1000 milliseconds. So for these 1000 milliseconds, the built-in LED will stay as high. Okay. Once, as soon as 1000 milliseconds pass, the next line will be executed, which is digital write, uh, pin name and low. I mean, after staying high for 1000 milliseconds, it will turn back off. Okay. After that, we give another delay of 1000 milliseconds. I mean, it will stay low for 1000 milliseconds. Now here's the thing, the most important thing: void setup runs only once. Okay, let me just simply runs only once. Okay, void loop. Yeah. So void setup, as soon as you give power, as soon as you code this microcontroller and give power to it, void setup will run just once, whereas void loop will run till the power supply is cut off. Okay. Now, as we are done with code, we'll start simulation, and we have a simulation timer also. As you can see, here is the built-in LED. It is blinking. I mean, it will stay on for 1000 milliseconds, which is 1 second, and it will turn off for 1000 milliseconds. Okay, and this is the LED which is used to determine whether the Arduino Uno is on or off. And there is a simulation timer also, and you can stop simulation and you can drive your required results. Some important things in then it will be initialized again and again, right? Sam fan. So if we write some important things in loop, then it will be initialized again and again, right? I didn't get your question. Some important things in loop. Yeah, exactly. Yeah, it doesn't matter what sort of function, what sort of operations which you want to do. If you put that operations in void loop, It will keep on running till the power supply is cut off. Okay. Now we'll try to include some other components and we'll try to code them if time permits. Okay. Now let's take an LED. I'll take an LED and I'll drag and drop. Okay. Now we'll take a resistor and I'll place it over here. Okay. Now we'll start connecting it. The reason I'm placing the resistor is from this we get from the digital pins we get an output of 7 volts, but for an LED if we give 7 volts directly the LED won't work. I mean it will simply burn off. That is the reason we are including a resistor also. I'll rotate this and we'll start connecting it. So we'll connect the cathode with the resistor and we'll connect the resistor to any sort of any digital pin, let's say fourth. Next you have to connect this anode to the ground we have over here. Yes. So now the LED, I mean the circuit is done for now. Next we'll try to code this. I'll show you how to code this from scratch. We'll simply delete this. Next, as you can see, the positive pin of the LED is connected to the fourth pin. Okay, so to the LED we are giving power from the fourth pin. So let's define that first. For that, int LED is equal to 4 semicolon. Okay. Next we'll start void setup first. Next pin mode. Open your brackets. Next, I have defined the fourth pin as LED, so I can simply use LED over here, comma output. So through this, we are informing that from the fourth pin, the Arduino Uno has to give output. Okay. Now I can simply close the parenthesis. Next, open void setup, void loop. Again, open parenthesis. Here, first, as I said, default output from the Arduino will be low. So the first instruction will be digital write. Open the brackets. Then the pin name, which is LED, comma high. Uh, Note one thing: these sort of expressions, output high or low, these are supposed to be in higher case, uppercase. Okay, a semicolon. Next, we'll give a delay of 1000 milliseconds, of course. Next, we give digital write LED, comma LOW. Next, a delay of 1000 milliseconds again. Next, close. Okay, now that we are done with the code, let's check for any mistakes. I don't think it should work. Yeah, wait a moment. My bad. We need to give the resistance also. 220. That be good. Start simulation. No, the resistance is too high. So that's 150 maybe. simulation. What happened? Just a moment. Let me figure it out. Did I give my connections wrong? Yeah, I was. I didn't give the corrections right. As you can see, the LED is blinking for LED is staying on for 1 second, and it is staying off for another second. Okay, that is how you use KiCad. You use Tinkercad. I'll show you around a few of my projects which I did in this tool. We'll go to designs and circuits. Yeah, this was a design which I made to interface a motor driver, Arduino Uno, and a stepper motor. I should have included a resistor over here, and here is the code for it. And if I start simulation, the input power to the motor driver is way too high, so it will simply burn off. You see, and when this symbol appears on the component, it indicates that the load is way too high or the input power is way too high. Okay, so that was one of my projects, and yeah, here are a few more projects. The only disadvantages of this is if you don't find your required component in this software, in this tool, you cannot import or export from any other software. I mean, let's say it doesn't have a normal two-way switch. If I click a switch, the only switches it shows us push button and slide switch. Okay, but I don't find normal switch over here, two-way switch or a one-way switch. That's a disadvantage. If I want to include a two-way switch or a one-way switch, I cannot. I need to use some other software again. In Tinkercad, I cannot do it. So you have to do, if you want to use Tinkercad, you have to use it only when all the components which you need are available in this. Okay. Else, if you don't want to use this, you can use Proteus also. In Proteus, you can include external libraries, but that's a pretty complex software. It's not really for beginners. A lot of expertise is needed. I don't hold a lot of expertise in that also. All you have to do is install the software, then you can download libraries from GitHub, then you copy paste those libraries in the program files, and then you can access the libraries. And you have to use some external softwares to code those components separately. You have to again export the code from that software into Proteus. Then you have to run simulations. That's a pretty complex, professional level software which is used. So we'll leave it away for now. That's it. I want to show you another useful tool. It is mainly helpful for CAD. Let me just share my screen again. Uh, Yeah, this is the tool I was talking about, GrabCAD. I mean, if you don't have enough time to design your own models like these, you can simply import them from online. All you have to do is find the relevant file extensions or the file formats you have to. All you have to do is search for GrabCAD, click on library, and these are all the models which they have. There are a lot of models, and not only for Fusion 360. If you need any other, if you need this for any other softwares also, for example, SolidWorks or AutoCAD, you can do it. Uh, for example, I need a gear. I'll search for it, and I'll find a few relevant models. And here you can see SolidWorks, Step or IGS, and those are the file extensions which this particular tool has. And you can also select the software or category which you need. For example, if you need for Fusion 360, you can select Fusion 360 in this drop down, and yeah, gears related to Fusion 360 will be displayed. Okay, for example, this I click on that, and then if I want to download files, it will ask for something. I forgot my password. I'm sorry for that. Once you download that, a zip file will be downloaded. From that, you need to export the models. Then you have to go back to your Fusion 360. Then click on Data Panel and click on Assets and click on Upload. Once you click on Upload, you can simply import, the libraries which you downloaded, the libraries which you download from GrabCAD, and then you unzip the file, and then you can include that into this. And here are a few things which I already imported. This is a soap dispenser. It takes a time to render, but yeah. Yeah, this model I imported. I downloaded it from GrabCAD. I unzipped it and I imported it to Fusion 360. On this, you can further apply whatever operations or whatever tools you want to use on this. It saves a lot of time, and it simply becomes more easier. Else, but I recommend you to design everything from scratch, because once you import this, I imported this bottle, but I cannot customize this properly. Okay, if I want to change the height or size of this, I cannot change that. It comes in with a default size, and it stays that way till the end. You cannot change the size. If you want to customize yourself, if you want to change, uh, you know respectively with the situation, then I recommend you to design your models from scratch. Okay. uh, yeah, any more doubts? Cathode to ground. Yeah, I did that. I test account. I didn't get your question. Cathode to ground. Yeah, I think I get your question. It might be a glitch in the it might be a glitch in the tool, but there's something called as, if it works, just leave it alone. That's what I applied over there. Okay. Any other doubts? It should be a glitch actually. I worked on a lot of projects using Tinkercad, but I never faced that particular problem. Any more doubts, or any more recommendations which you would like from me regarding hardware? If there are no doubts, I think I'm done with the session.
Hello. Yes, am I audible?
Yeah, you are.
Yeah. So again, thank you for the session. It was a great one. And does anyone have any other questions? You can drop them right now. And yeah, if anyone has any questions, you can drop them right now, and the speaker will answer it for you.
Else, if you
So
need any
let's
sort
wait.
of resources regarding Fusion 360 or KiCad, I have a few resources. I write blogs on Hashnode. If you want, I can share you the links of them. I'll share it with the organizers. You can forward them to the people who need.
Yeah. So if there are no more questions, let's wait for 2 minutes. If there are no more questions, then I believe we can end the session. And yeah, in the meantime, let's say you designed a PCB using,
Okay.
you know, your editor. How would you go about programming that PCB?
You have to, like, you cannot test a program on a PCB while designing it. A PCB, you can only simulate the electrical part of the PCB. You cannot simply program it. For that, you have to do it. You have to prototype a PCB first, then you have to simulate that manually again. You have to prototype PCB, then print it, then code it manually, and then you have to simulate it again. There's no way to separately take a PCB and program it and then do it using some software tools. Okay. If you really want to, then you can simply use Proteus. You can design a circuit in that. You cannot design PCBs there. You can design a circuit, then you can program it, and then you can test your program if it works or not. But there's no way you can program PCB without using any manual interaction.
Okay. Yep. So I don't think there are any more questions, and I believe we can end the stream now. Once again, thank you, Sudhansh, for taking this great session on hardware.
It's
And
fine.
the feedback form link will be sent in the WhatsApp group. Uh, be sure to fill it out and use whatever you learned today and create a simple project and send it to us. So with the hashtag LHWSNIST. So if you send challenges through the feedback form, then you get points and you also get to showcase your learning. So if there is, would you like to add anything else?
Me, yeah. Just try to use your time in fun stuff. Don't really, I know it's pretty awkward to tell that put on some time on academics on your career, but spend some time with your loved ones, do some pursue your hobbies, but spend a bit of time on tools and learning the technologies which are currently in the market. Okay. Technologies often get updated every 10 to 15 years, so you have to catch up to it. Then only you can Put up a path for a bright career further, and don't just get limited to one single tool or one single domain. Try to learn a lot of things so that you can have a much more broader perspective when you go out of the college.
Yeah, great advice. Like really applies to basically anything in technology, not just
Yeah,
hardware.
yeah,
It applies to any domain in technology. So on that note, I believe we can end it.
yeah, sure.
Once again, thank you for taking this session. It was a
Yeah, thank
great
you
one.
for you too
I
for
personally,
taking
yeah,
the session. Yeah,
yeah, I personally learned a lot about that. I didn't know about Tinkercad. I used to do a
glad
bit
to know
of
that.
programming. Yeah, yeah. So thank you,
Yeah,
and yeah, signing off.
bye.
Bye.